It is April 1970, and the Apollo 13 spacecraft is dying.
Yeah, dying fast.
Right. The oxygen tanks have ruptured, the power is draining, and you have these 3 astronauts crammed into a lunar module that was, really only designed for 2.
And the immediate threat isn't even a lack of oxygen.
Exactly. It is their own breath. They are slowly suffocating on the carbon dioxide they're exhaling. The environmental life support systems, those multi-million-dollar systems, have completely failed.
The lithium hydroxide canisters are just depleted. Done.
Right. So what saves them? It's this hasty, improvised contraption built from plastic bags, cardboard, duct tape, and the chemical properties of this exact same humble white powder sitting in a yellow box in the back of your refrigerator right now.
It is kind of amazing to think about.
It really is. So welcome to this deep dive. Today, we are taking you on a deeply immersive mission into this massive stack of technical data, historical texts, and, rigorous scientific studies, all of it centered on a single, deceptively simple molecule.
The CO3.
Yep, sodium bicarbonate.
And we're really going to look at a compound that defies our standard expectations of chemistry here. Because usually, a chemical has a designated lane, right?
It's a fuel or a solvent or whatever.
Exactly. But this particular molecule is uniquely versatile. So we're going to be looking at endothermic thermodynamics, the cellular biochemistry of muscular fatigue, the quantum mechanics of identifying impurities, and even the molecular dynamics of putting out industrial fires.
It is basically the Swiss Army knife of the molecular world. But before we get into how it delays muscle failure in Olympic sprinters or how it suffocates a roaring chemical fire, I really want to understand what this stuff actually is.
The physical properties.
Yeah, because looking at the data sheets from AGC Chemicals, it just looks like a standard, boring, inorganic salt.
Well, let's pull the microscopic blueprint apart, right? Sodium bicarbonate has a molecular weight of 84.01.
Okay.
And its true specific gravity sits at 2.22. Though, you might see industrial suppliers like WLT distributors listed around 2.16 grams per cubic centimeter.
Wait, so why the difference?
It really just depends on the packing density and the purity of the bulk product.
Okay, so specific gravity of 2.22, that means it's, what, more than twice as dense as water?
Yeah, precisely.
Because if I have a cubic centimeter of water, it weighs 1 gram. So a cubic centimeter of pure solid sodium bicarbonate weighs 2.22 grams. It's actually surprisingly heavy.
It's a very dense crystalline structure.
Yeah.
And its specific heat, which is the thermal energy required to raise the temperature of 1 mole of the substance by 1 degree Celsius, is 20.94 calories per degree mole at room temperature.
20.94.
Got it. But the dynamic behavior, the really interesting stuff, begins when you introduce it to water. The solubility curve is highly temperature dependent.
Okay, how so?
Well, at freezing, 0 degrees Celsius, you can dissolve about 6.5 grams of it into 100 grams of water.
Meaning, like, if I dump 10 grams in, 6.5 grams dissolve, and the other 3.5 grams just sit on the bottom of the glass as sludge.
That's exactly it. Now, if you bring that water up to room temperature, say 25 degrees, the kinetic energy of the water molecules increases. Right?
Yeah, they're moving fast.
And that solubility jumps to 9.4 grams. Then push the water to a hot 60 degrees Celsius, and it spikes to 16.4 grams per 100 grams of water.
Okay, but wait, I did notice a discrepancy in the provided material here. One of the industrial tables listed the 60-degree solubility at 13.8 grams, not 16.4. What's going on there?
Yeah. That variance usually points to the difference between a purely theoretical laboratory measurement and the behavior of an industrial-grade product.
Oh, because the industrial stuff isn't perfectly pure.
Exactly. It might contain trace amounts of sodium carbonate or just moisture that alter the equilibrium state of the solution. Oh, and it's also completely insoluble in ethanol.
Wait, really? Not at all?
Not at all. You can drop a crystal of it into pure alcohol and it will just sit there indefinitely, which is a classic characteristic of this type of inorganic salt.
I guess that's a very useful property when chemists need to wash or purify a sample without dissolving it, right?
Yeah, highly useful.
Okay, so it dissolves in water, doesn't dissolve in alcohol. But looking through the chemistry stack exchange discussions in our sources, there was a question from a user that genuinely stumped me.
The one about the formula.
Yes. They pointed out the chemical formula, NaHCO3. Sodium, hydrogen, carbon, oxygen. There is a hydrogen atom sitting right in the middle of it.
Right.
And if I remember basic high school chemistry, substances that have a hydrogen atom to give away are acids. So why is this stuff almost universally called a weak base?
That user hit on the exact reason this molecule is so chemically fascinating. To understand this, we have to look at the Brensted-Lowry theory of acids and bases.
Okay, remind me how that works.
Well, in that framework, an acid is a proton donor. It wants to give a hydrogen ion away. A base is a proton acceptor. It wants to steal a hydrogen ion from its environment.
So it's basically all about who wants the hydrogen proton the most.
Yes, exactly. And the bicarbonate anion, the HCO3 minus part of the molecules, what we call amphoteric or amphiprotic.
Meaning it goes both ways.
Yeah, it's a chemical chameleon. Because it holds that single hydrogen atom, it technically has the ability to act as an acid. It can donate that proton to a strong base.
And what's left behind if it does that?
It leaves behind a carbonate ion, CO3, with a -2 charge.
But it usually doesn't do that.
No, in a standard aqueous solution, its tendency to act as a base completely overpowers its acidic potential. It prefers to accept a proton from the surrounding water molecules.
To become what?
To become carbonic acid, H2CO3.
That is so weird. It looks at the water and says, I know I have one hydrogen, but I'm going to take one of yours anyway.
It's greedy. And here is the crucial mechanical step. Carbonic acid is highly unstable.
Oh, so it doesn't stay carbonic acid for long.
Not at all. The moment the bicarbonate steals that proton to become carbonic acid, the new molecule instantly breaks apart into water, H2O, and carbon dioxide gas, CO2.
So it just bubbles away.
Right, and by stealing that proton from the environment to trigger this breakdown, it is actively consuming free hydrogen ions from the surrounding solution. Lowering the concentration of hydrogen ions means raising the pH, and raising the pH is the literal definition of a base.
That is brilliant. It's essentially a vacuum for acidity. It sucks up the free hydrogen, turns it into a gas, and bubbles it away out of the liquid entirely.
It adapts its behavior to neutralize whatever chemical environment it finds itself in. And this chameleon-like ability is what governs its most crucial thermodynamic behavior.
Because what happens when we force this weak base to collide with a highly aggressive, strong acid?
The physics involved become incredibly counterintuitive.
I really want to dig into that.
Yeah.
Because the bench-temp technical protocols in our stack highlighted something that seems to just break the rules.
A thermal trap.
Yeah, normally if I take a strong base, like sodium hydroxide lye, and mix it with a strong acid, like hydrochloric acid, the reaction is violent. It's highly exothermic.
Oh yeah, the beaker gets dangerously hot. Neutralizing an acid like that releases a massive amount of thermal energy.
Right. But when you neutralize hydrochloric acid with sodium bicarbonate, the protocol notes it is an endothermic process. It absorbs heat.
Yes.
The heat of dissolution is 17.1 kilojoules per mole, or 3.81 kilocalories per mole. If I'm holding that beaker, I'm not feeling it get hot. I'm feeling the glass turn ice cold in my hand.
Exactly.
Why does this specific neutralization steal heat instead of creating it?
It comes down to the thermodynamic accounting of breaking bonds versus making bonds.
Okay.
To neutralize the acid, the sodium bicarbonate crystal lattice must first be torn apart. That requires a significant investment of energy, which we call lattice energy.
So it takes energy just to unpack the box, basically.
Right. Then the bicarbonate anion reacts with the acid to form that unstable carbonic acid we just talked about,
Which immediately undergoes that violent phase change.
decomposing into liquid water and carbon dioxide gas. So it's doing a lot of structural work.
A tremendous amount.
The energy required to dismantle the crystal, drive the formation of the intermediate acid, and force the expansion of a gas into the atmosphere. It's significantly greater than the energy released when the final products form their new bonds.
The final products being the sodium chloride, salt, and water.
Exactly. So the chemical math is running at a deficit. To pay that energetic debt and drive the reaction forward, the system has absolutely no choice but to absorb ambient thermal energy from the surrounding water and the glass of the beaker.
It is literally a heat vampire. It refrigerates its own environment to fuel its destruction.
It really does.
But beyond the weird temperature drop, this reaction is the foundation of something called buffering capacity. The source materials throw out a lot of calculus to describe this, specifically the Greek letter beta.
Yes, the buffering capacity, beta.
How do I, as a non-chemist, visualize a buffering capacity?
Think of buffering capacity as a mathematical measurement of stubbornness. It is a solution's resistance to having its pH changed.
Okay, stubbornness.
If you have a beaker of pure, unbuffered water at a neutral pH of 7, and you add a single drop of strong hydrochloric acid, the pH will instantly crash down to 3 or 4.
Wow, that fast.
Yeah, the water has zero resistance.
It's like a car hitting a massive pothole with no suspension. You feel the entire impact instantly.
I like that analogy. A buffer is the suspension system.
Mm.
The benchchem texts define the suspension with the formula for beta.
The calculus part.
Right. Beta equals the derivative of the concentration of strong base added over the derivative of pH. So beta equals dB over dpH.
Okay.
Or, looking at it from the other side, negative dA over dpH, where A is the moles of strong acid.
So for those of us who haven't taken calculus in a decade, what does that derivative actually mean in a physical beaker?
It is asking a very practical question. Exactly how many moles of a corrosive acid do I have to pour into 1 liter of this buffered solution just to drag the pH down by one single solitary unit?
Oh. How heavy does the payload have to be to compress the shock absorber by 1 inch?
Exactly. And chemists map this out using an experimental setup called a potentiometric titration.
How does that work?
Imagine a glass beaker containing our sodium bicarbonate solution. Submerged in the liquid is a combined glass electrode connected to a highly sensitive pH meter, and it's stirring continuously on a magnetic plate.
Right.
Above the beaker, suspended on a stand, is a long graduated glass tube called a burette, filled with a standardized 0.1 molar strong acid.
Usually hydrochloric acid.
Often, yes. And you just slowly open the valve and drip the acid in.
Drop by drop.
Drop by drop. And as you add the volume of acid plotting that on your x-axis, you plot the resulting pH on the y-axis.
Right, so you're graphing it in real time.
You're creating a visual curve of the solution's stubbornness. When you start dripping the acid into the bicarbonate buffer, you'd expect the pH to drop. But it doesn't.
Because the shock absorber engages.
The curve stays almost perfectly flat. You are pouring acid in, and the pH refuses to budge.
Because every single hydrogen ion you drop into the beaker is instantly being grabbed by the bicarbonate.
Yes. Converted to carbonic acid and bubbled harmlessly out of the beaker as carbon dioxide gas.
That's amazing.
The calculus shows that this resistance, this beta value, is at its absolute maximum when the pH of the solution matches the pK value of the buffer itself.
And it will hold that flat line indefinitely.
No. Eventually, you run out of bicarbonate molecules. You exhaust the chemical reservoir.
Ah.
When that last molecule of bicarbonate is consumed, the shock absorber snaps. The next single drop of acid has nothing to react with, and the pH plummets off a cliff.
Just a straight vertical drop.
That sudden vertical drop on the graph is called the equivalence point.
Okay, so a chemist in a lab uses this shock absorber to control experiments. But what absolutely blew my mind reading the exercise physiology data is that this exact same calculus equation, the same beta capacity, is what dictates the limits of human athletic endurance.
Yes, we are stepping out of the glass beaker and into human biology.
It's happening inside the blood of an Olympic sprinter.
To comprehend why athletes consume baking soda as a performance enhancer, we have to isolate the biochemistry of muscle fatigue. What is physically happening when a muscle burns and fails?
Right. Because for a long time, people just said, lactic acid builds up and left it at that. But the cellular reality is much more aggressive.
Much more.
During a high-intensity exercise, like a 400-meter sprint or lifting a heavy weight, the muscle needs a massive amount of ATP, the cellular energy currency, and it needs it immediately. So it uses anaerobic glycolysis.
It splits glucose to generate that rapid energy. But the metabolic consequence of running that high-speed glycolytic engine is the massive accumulation of hydrogen cations, H+ ions, alongside the lactate.
Free protons, acid.
Thousands of them flooding the microscopic environment of the skeletal muscle fiber. A resting muscle has an intramuscular pH of about 7.1.
Which is pretty neutral.
But during intense exertion, that localized pH plummets down to 6.5 or even lower. This state of severe intramuscular acidosis physically breaks the machinery of the muscle.
Wait, how does acid stop a muscle from contracting?
A muscle contraction relies on actomyosin cross-bridges. Think of them as microscopic mechanical oars that grab onto a fiber and pull, creating force.
Okay, microscopic oars.
Those oars rely on calcium ions to trigger their movement. But when the muscle floods with hydrogen ions, the acid physically competes with the calcium.
Oh, so they fight for the same spot.
The hydrogen binds to the receptors blocked in the calcium, and the oars can no longer grab the fiber. Furthermore, the high acidity alters the shape of key glycolytic enzymes, effectively turning off the glucose-burning engine.
So the burning sensation and the sudden catastrophic inability to produce force isn't your brain giving up.
No, it is localized chemical failure.
The muscle is quite literally drowning in acid, and the gears are jamming, so athletes try to fix this by swallowing a dose of sodium bicarbonate before the race.
They do.
But here's the disconnect in the literature that confused me. The baking soda goes into your stomach, absorbs into your blood, and raises the pH of your blood. But the texts explicitly state that the skeletal muscle cell membrane is highly impermeable to the bicarbonate anion. The buffer cannot get inside the muscle where the acid is actually doing the damage.
Right, it stays outside.
So how does a buffer in the blood help a muscle cell that it can't even touch?
Through an incredibly elegant biological workaround called dynamic buffering. It relies entirely on concentration gradients.
Okay, how does that work?
On the outer membrane of your muscle cells, the sarcolemma, you have thousands of specialized transport proteins called monocarboxylate transporters, or MCTs.
What's their job?
They're essentially bilge pumps. Their sole function is to grab the toxic hydrogen ions and lactate from inside the muscle cell and pump them outside into the bloodstream, clearing the intracellular environment.
Okay.
Now imagine a crowded stadium. If the hallway outside the stadium doors is jam-packed with people, nobody can exit. The flow stops.
Right.
If the blood is already highly acidic from exercise, the MCT pumps struggle to push more acid out into an already crowded environment.
But if I ingest baking soda, the bicarbonate circulating in my blood acts like a vacuum. It neutralizes the acid in the blood, effectively emptying that hallway.
You are artificially widening the pH gradient between the inside of the muscle and the blood. Because the blood is now highly alkaline and devoid of acid, the MCT pumps go into overdrive.
So they just pump faster.
They can suck the hydrogen ions out of the muscle cell at a vastly accelerated rate. The bicarbonate acts as a systemic sink, aggressively pulling the fatigue-inducing fire out of the working tissue without ever needing to cross the cell membrane.
You artificially delay the point of chemical failure?
Exactly.
That is wild. It's indirect life support for the muscle. And there was a fascinating tangent in the open access repository data regarding intracellular buffers.
Oh, yeah.
We know bicarbonate handles the blood outside the cell, but what's handling the acid inside? The data listed the pK values of various amino acids, and it specifically highlighted histidine, which has a side chain pK of 6.00.
Yes, 6.0.
Why is that specific number so important?
Because it sits right in the danger zone. We just discussed that an exercising muscle drops from a pH of 7.1 down to 6.5.
Right.
If an athlete has high levels of a dipeptide called carnosine inside their muscle tissue, which is synthesized from beta-alanine and histidine, that histidine side chain becomes active.
Because its pKa is 6.00.
Yes, it reaches its maximum buffering capacity, its stiffest shock absorber state, right as the muscle is crashing into catastrophic acidosis.
So histidine fights the fire inside the cell, while the ingested bicarbonate pulls the smoke out into the blood.
That's a perfect way to describe it.
But there's a massive, uncomfortable catch to ingesting baking soda for athletic performance.
The gastrointestinal distress.
Yeah. You are taking a pure powdered base and dumping it down your esophagus into a vat of hydrochloric acid inside your stomach.
And we already talked about what happens when you mix those two things in a beaker.
It violently produces carbon dioxide gas,
Massive, rapid expansion of gas inside the human digestive tract.
which means severe cramping, intense bloating, and explosive biological consequences.
Yeah, it's not pretty.
If you are a sprinter on the starting blocks of the Olympic finals, the absolute last thing you want is catastrophic gastric distress.
Which is why researchers are constantly looking for ways to cheat the delivery system. Enteric-coated capsules are one method, designed to survive the stomach acid and dissolve only in the more neutral environment of the small intestine.
And that brings up the bariatric surgery case study from the Sports Science repository.
That was a fascinating case.
This was a patient whose stomach had been surgically altered, effectively bypassed for weight loss reasons. The researchers realized they had a unique opportunity.
Right. They asked if the limiting factor of sodium bicarbonate supplementation is the violent CO2 production in the stomach, what happens if the stomach is completely out of the equation?
Does the buffering effect become pure, unadulterated performance fuel?
And the results of that physiological bypass are revealing. When the bicarbonate is delivered directly to the intestine, avoiding the gastric acid bath completely, there is no localized gas production.
None at all.
The absorption into the systemic circulation is smooth and highly efficient. The dynamic buffering gradient operates at maximum capacity, pulling the acid from the muscle, but the athlete experiences none of the crippling nausea.
That is incredible.
It proves that the human body possesses a much higher ceiling for muscular endurance than we usually experience. Our limits are often dictated not by mechanical muscle failure, but by our inability to manage the localized acid-base chemistry.
We are utilizing this white powder to extinguish a microscopic biochemical fire of lactic acid. But what stuns me is that the exact same endothermic properties, the exact same thermal decomposition, and the exact same release of CO2 gas are utilized by engineers to fight literal, roaring industrial fires.
Oh, absolutely. The YRC chemist technical specifications outline the use of sodium bicarbonate as a critical, highly engineered component in specialized dry chemical fire suppression agents.
And we are specifically looking at Class B and Class C fires here, right?
Yeah.
Class B being flammable liquids and gases, a ruptured fuel line, a massive gasoline spill on a tarmac. And Class C being energized electrical fires, like a server room or a high-voltage transformer explosion.
Correct.
If I am a firefighter looking at a burning pool of jet fuel, my instinct is to spray water on it. Why is that a terrible idea?
Water is a catastrophic choice for both of those.
Yeah.
If you spray high-pressure water onto a burning liquid fuel, the water, being denser, sinks below the fuel.
And then what?
It instantly boils into steam and violently scatters the burning liquid over a wider area. You don't extinguish the fire, you aerosolize it.
Oh, wow, making it worse.
Much worse. And for Class C fires, water conducts electricity. Spraying a hose at a burning transformer is a fast track to electrocuting the firefighter. You require a non-conductive, specialized dry agent.
So we deploy the powder. But let's look at the chemistry of this attack. You spray a cloud of sodium bicarbonate into a wall of flame. I'm playing devil's advocate here. Aren't you just blowing a dry powder into a drafty fire? How does a powder physically stop thousands of degrees of combustion?
It employs a highly sophisticated dual mechanism attack. The first mechanism is chemical inhibition.
Okay.
Let's return to the thermal decomposition profile we established at the beginning. When sodium bicarbonate is heated to 270 degrees Celsius, it violently breaks apart.
Right. And the flame front of an industrial fire is well over 1,000 degrees.
Exactly. So the powder hits the heat and instantly shatters. And remember the thermodynamics.
That decomposition is endothermic?
Yes. It requires a massive influx of thermal energy to break the molecular bonds. As millions of microscopic powder particles enter the flame, they simultaneously undergo this phase change, literally stripping massive amounts of heat out of the fire just to fuel their own destruction.
It acts as a massive thermal sink. It basically refrigerates the fire.
Furthermore, as it decomposes, it exhales a dense cloud of carbon dioxide gas directly into the heart of the combustion zone.
And fire requires oxygen to sustain itself.
Right. The sudden localized release of CO2 heavily dilutes the ambient oxygen concentration, suffocating the reaction.
But the texts argue that the most lethal part of the attack isn't the cooling or the gas, it's the residue. When the baking soda breaks down, it leaves behind sodium carbonate, Na2CO3.
The chemical scavenger.
Yeah. To understand why sodium carbonate is so lethal to a fire, you must understand how a flame propagates, right?
Combustion is a chain reaction sustained by free radicals. These are highly unstable atoms or molecules with unpaired electrons. They frantically jump between fuel and oxygen molecules, tearing them apart and releasing energy.
They are the chaotic sparks keeping the engine running.
The microscopic sodium carbonate residue left behind by the powder actively hunts these free radicals.
Really? How?
It provides a stable surface for the free radicals to bind to, effectively trapping those unpaired electrons and removing them from the combustion equation.
Wow.
It severs the chain reaction at the quantum level. The fire doesn't just cool down, it chemically forgets how to burn.
A microscopic chemical assassin. So that's the chemical inhibition. What is the second mechanism?
Physical smothering. When the agent is discharged from an extinguisher, propelled by high-pressure nitrogen gas, it doesn't just shoot out in a straight line.
It spreads out.
It is engineered to form an incredibly dense, billowing cloud. As the heavier particles begin to settle, they lay down an impenetrable physical blanket over the surface of the liquid fuel.
Like throwing a heavy wool blanket over a campfire.
It creates a physical barrier that separates the flammable vapors rising from the liquid pool from the atmospheric oxygen above. No oxygen interface, no combustion.
That makes sense.
And crucially, this blanket remains in place, preventing the superheated metal or ambient heat from causing a reignition.
But reading the engineering specs for manufacturing this powder, it is terrifyingly rigorous. I can't just take a cardboard box of baking soda from the grocery store, throw it at a burning jet engine, and expect it to work.
No, absolutely not.
The manufacturing texts go on a massive tangent regarding PSD particle size distribution. Why does the physical size of the dust grain matter so much?
Because particle size distribution dictates the fluidization and expansion mechanics of the agent. If the manufacturer grinds the sodium bicarbonate too coarsely, The particles are too heavy.
Well, so what happens?
When sprayed, they won't suspend in the air to form a cloud. They will just act like sand, dropping straight to the ground and failing to interact with the flame front.
Okay, so just grind it down into an ultrafine microscopic dust.
Well, if you mill it too finely, the particles lack the mass and momentum required to penetrate the violent thermal updrafts of a roaring fire. The heat will just blow the microscopic dust away before it ever reaches the combustion zone.
So it has to be the perfect Goldilocks size.
Furthermore, an optimal, tightly controlled PSD ensures fluidization. When the pressurized gas hits the powder inside the metal cylinder, the powder must flow through the internal siphon tube and out the nozzle as smoothly as liquid water.
Without clogging or clumping, which brings up the moisture control standards. They are obsessive about keeping this powder dry.
Sodium bicarbonate is highly hygroscopic. It loves to attract and absorb ambient water vapor from the air. Right? If an industrial fire extinguisher is mounted on a factory wall for 5 years, and there's even a fraction of a percent of moisture trapped inside that cylinder, the powder will slowly absorb it and cement itself into a solid, impenetrable brick.
So a fire breaks out, the worker pulls the pin, squeezes the handle, and just gets a hiss of gas while the powder stays cemented in the tank.
A fatal failure. To prevent this, the manufacturing process requires extreme drying protocols, ensuring a purity of over 99%.
That is intense.
The particles are then meticulously coated with specialized silicone-based anti-caking agents, ensuring that even after a decade in a steel tank, the powder remains perfectly free-flowing and lethal to combustion.
So deploying a dry chemical extinguisher isn't just throwing dirt on a fire. You are deploying a highly engineered, moisture-proofed, dual-mechanism assassin that simultaneously freezes the environment, starves the oxygen, hunts down free radicals, and drops a physical barricade over the fuel source.
It systematically dismantles the fire triangle: heat, fuel, and oxygen simultaneously.
Here is the pivot that I find conceptually hilarious. We have just established how violent thermal decomposition violently tears apart the physical chemistry of a fire to save a factory from burning down.
Yes.
But if I take that exact same chemical, relying on that exact same thermal decomposition, I can use it to construct a delicate, airy sponge cake in an oven.
We are harnessing the exact same thermodynamic phase change, but instead of using it for destruction, we're using it for structural engineering. Welcome to the culinary science of chemical leavening.
Drawing from the baking sense technical guides in our sources, our first order of business is establishing a strict boundary line between baking soda and baking powder.
They're fundamentally different chemical systems, and using the wrong one will ruin a kitchen.
Right. Baking soda is what we've been talking about. Pure sodium bicarbonate, a pure, weak base. If I mix pure baking soda into a bowl of flour and water, nothing happens chemically. It just sits there.
To activate the gas release at room temperature, it requires the introduction of an external acid.
The baker must provide the proton donor. Ingredients like buttermilk, which contains lactic acid, brown sugar, which contains molasses, or yogurt.
Exactly. When the pure base encounters the acidic ingredient in the aqueous environment of the wet batter, the neutralization reaction we discussed in Section 2 occurs,
They neutralize each other.
dropping the shock absorber and releasing a slow, steady stream of carbon dioxide gas bubbles.
And because the batter is full of flour, those bubbles get trapped. The gluten proteins in the flour form an elastic web, like a balloon, capturing the CO2.
Right.
When the heat of the oven sets the proteins, the bubbles solidify into the airy texture of a cake crumb. But what if I screw up the chemistry? Let's say I find a recipe that calls for regular milk, flour, and white sugar, no acidic ingredients at all, and I accidentally dump in a tablespoon of pure baking soda.
You have removed the neutralizing acid from the equation, the batter goes into the oven, and it relies entirely on the ambient heat to force the chemical reaction. Eventually, the oven reaches that critical threshold, and the baking soda undergoes thermal decomposition, releasing the CO2 to lift the cake.
So the cake still rises. What's the problem?
Look at the byproduct. When sodium bicarbonate decomposes under heat without an acid to neutralize it, it leaves behind sodium carbonate, Na2CO3. We just discussed how this residue is a lethal alkaline scavenger in a fire. In a baked good, that highly alkaline compound remains embedded in the crumb of the cake.
Yuck.
It yields a distinctly soapy, metallic, and incredibly bitter flavor profile. It essentially tastes like you baked a battery.
And it doesn't just ruin the taste. The source texts highlight that it physically alters the color of the food through bizarre visual chemistry.
Extreme pH shifts alter the molecular structure of natural pigments. If your batter contains natural non-Dutch cocoa powder, the excess alkaline environment reacts with the cocoa, turning it a deep, almost unnatural, reddish mahogany hue.
Which is where the name Devil's Food Cake comes from. I always thought it was just a marketing term for a rich chocolate cake.
A lot of people do.
But historically, the red color was the visual evidence of a chemical error, too much unneutralized baking soda in the batter.
It also wreaks havoc on fruit. The anthocyanin pigments in blueberries act as natural pH indicators. In their natural, slightly acidic state, they reflect blue or purple light.
Right, they look blue.
But if they are dropped into a highly alkaline muffin batter laced with excess sodium carbonate, the molecular structure of the anthocyanin shifts, changing the wavelength of light it absorbs. The blueberries will emerge from the oven a murky, unappetizing green.
Nobody wants a soapy green blueberry muffin. So to idiot-proof the baking process and guarantee that all the base gets completely neutralized, food scientists invented baking powder.
Baking powder is a self-contained, all-in-one chemical leavening system. It contains both the base sodium bicarbonate and a dry powdered acid, perfectly mathematically balanced so that they completely neutralize each other.
Leaving zero soapy residue behind. The technical ratios for mixing your own emergency batch are actually quite simple. If you run out, you mix 1 part baking soda, 2 parts cream of tartar, and 1.5 parts cornstarch.
That's the classic ratio.
But the text includes a massive warning about this homemade mix. It notes that cream of tartar is a single fast-reacting acid, and it warns that the second you mix the wet and dry ingredients together, you have to rush the batter straight into the hot oven. Why the panic?
We have to look at the temporal dynamics of leavening. Cream of tartar potassium bitartrate is highly soluble and incredibly aggressive.
Okay.
The absolute millisecond it comes into contact with the water in your batter, it dissolves, attacks the baking soda, and dumps its entire payload of carbon dioxide gas almost instantly.
The reaction happens in the mixing bowl, not the oven.
Precisely. If you let that batter sit on the kitchen counter while you prep your pans, the CO2 bubbles will rise to the surface, burst, and dissipate into the air.
So you lose all your lift.
By the time you put it in the oven, the chemical lift is exhausted, and your cake will bake into a dense, flat hockey puck. You have to rush it into the oven so the heat can gelatinize the starches and lock the gluten structure around the expanding gas before it escapes.
But when I buy a commercial tin of baking powder from the store, I don't have to rush. I can mix pancake batter, let it sit on the counter for 20 minutes, and it still works perfectly.
Because modern commercial baking powder is double-acting. It is a marvel of temporal chemical control. It contains not one, but 2 different dry acids.
Oh, too.
The first is a fast-acting acid, typically monocalcium phosphate. This reacts immediately upon hydration at room temperature, creating an initial burst of gas to lighten the batter and form microscopic seed bubbles.
Setting the foundation.
But the second acid is a slow-acting compound, like sodium aluminum sulfate. This chemical does not dissolve readily at room temperature. It lies dormant in the wet batter.
Sneaky.
It only activates and begins neutralizing the remaining baking soda when it reaches a specific high temperature inside the oven.
That is brilliant engineering. It gives you a second massive burst of structural gas right at the exact moment the heat is setting the walls of the cake to trap it. And what about the cornstarch? In the homemade formula, we added 1.5 parts cornstarch. What is the starch doing in a chemical reaction?
The cornstarch is an active chemical referee. Inside that tin of baking powder, you have a highly reactive base and a highly reactive acid sitting right next to each other, just waiting for water to start the fight.
Right, it's a powder keg.
If you open the tin on a humid summer day, ambient moisture from the air can seep in. Even a microscopic amount of water will trigger the reaction inside the container, ruining the entire batch. Cornstarch is a highly effective desiccant.
So it absorbs the moisture.
It aggressively scavenges and absorbs that ambient moisture, keeping the reactive powders dry and separated, drastically extending the shelf life of the product.
And when all this chemistry works perfectly, the bakers are aiming for a very specific structural metric. The Journal of Agroelementary Processes study included in our data measured the exact specific gravity of perfectly leavened cake batters. They determined the optimal target is between 0.8 and 0.85.
We discussed specific gravity earlier in terms of pure powder being heavier than water. In the context of a batter, it measures aeration.
Right.
Pure water has a specific gravity of 1.0. If the chemical leavening has successfully created enough internal gas bubbles, the density of the batter drops. A batter hitting 0.85 means it is physically lighter than water.
It is perfectly primed with trapped CO2, ready for the oven's heat to permanently lock that airy architecture into place.
Yes.
It is staggering to think about. This single molecule neutralizes severe acidosis in the blood of an exhausted athlete, mathematically flattens the pH curve in a laboratory titration, strips heat and free radicals out of an industrial fire, and meticulously aerates a sponge cake.
All the same molecule.
But none of these highly sensitive life or death reactions work unless the chemical itself is flawless. You can't put impure contaminated powder into an Apollo spacecraft scrubber or a commercial bakery. Where do we get it, and how do we guarantee its purity?
This leads us into the massive industrial apparatus required to supply the planet with sodium bicarbonate. Historically, and still today, it can be mined directly from the Earth.
Oh, you can just dig it up.
It occurs naturally as a mineral called nacolite, with massive subterranean deposits found in the Green River Formation, spanning Colorado, Wyoming, and Utah.
But mining isn't enough to sustain global demand, so we manufacture it synthetically. And the Chemistry LibreText source dedicated a massive section to something called the Solvay process. The authors highlighted this process as a historic marvel of green chemistry.
Yes, it is.
Now, when I picture a 19th century industrial chemical plant, I picture smokestacks, toxic sludge, and environmental devastation. Why is this specific process considered green?
It is praised for its atom economy and its elegant closed-loop recycling. The Solvay process is designed to synthesize sodium carbonate, which can then be easily converted to sodium bicarbonate using incredibly cheap, abundant raw materials.
Like what?
Sodium chloride, which is just saltwater brine, and calcium carbonate, which is common limestone.
Salt and rocks.
To force the reaction, the process introduces ammonia gas. The chemistry is complex, but the genius lies in the aftermath. The ammonia and the carbon dioxide used as intermediate catalysts in the reaction are not vented into the atmosphere or dumped into a river.
They reuse them.
The engineering of the plant captures those gases, recovers them almost entirely, and finally pipes them right back into the beginning of the synthesis loop.
So the plant feeds on its own exhaust.
Exactly. It minimizes hazardous chemical waste and maximizes the utility of every single atom entered into the system. It was one of the first massive industrial proofs of concept for sustainable, cyclical chemical engineering.
But once the white powder comes out of the Solvay plant, you have to prove it's pure. The laboratory testing protocols in the data are intense. They rely heavily on a technique called thermal gravimetric analysis, or TGA. How does heating something up prove that it's pure?
TGA is a beautifully simple concept executed with terrifyingly precise instrumentation. Imagine a microscopic scale inside an oven.
Okay, a scale in an oven.
You place an incredibly precise initial mass of your manufactured baking soda sample on the scale, say exactly 10,000 grams. You then fire up the oven, raising the temperature past that critical 270 degrees Celsius threshold.
We're forcing the thermal decomposition again? The phase change?
Yes. We know, based on inviolable stoichiometric laws, exactly what the molar mass of the resulting sodium carbonate, the water vapor, and the carbon dioxide gas should be.
Because the math is absolute.
As the sample cooks, the water and the CO2 boil off into the air, and the sample loses mass. The sensitive scale records this weight loss in real time. By measuring the exact mass lost, the chemist can calculate backward.
Oh, I see.
If you started with 10 grams, and the mathematical equation dictates you should be left with exactly 6.3 grams of sodium carbonate, but the scale reads 6.8 grams.
You know you have half a gram of garbage in your sample that didn't burn off?
You have irrefutable mathematical proof of contamination.
Okay, so TGA tells you that the batch is contaminated, but how do they figure out what the actual contaminant is? Because the next step in the text is quantum emission spectroscopy, and this sounds like science fiction.
It relies on the fundamental quantum mechanics of the atom. Let's say your TGA flagged an impurity, and you suspect the Solvay process was contaminated with metal salts.
Like calcium chloride or potassium chloride.
Right, or lithium chloride. To identify them, you introduce a sample of the impure powder to an extremely high-energy environment, typically a specialized superheated flame.
You literally set the powder on fire.
You are injecting raw thermal energy into the atoms. At the quantum level, the electrons orbiting the nuclei of these metal impurities absorb that thermal energy.
Right.
This absorption excites the electrons, forcing them to violently jump out of their standard orbits and leap into higher, unstable quantum energy states.
But they can't stay there forever.
No, the universe demands equilibrium. Almost instantly, those excited electrons collapse back down to their original, stable ground state. But energy cannot be destroyed. The energy they absorb from the heat has to go somewhere.
Right, thermodynamics.
So, as the electron falls back down, it ejects that exact packet of energy outward as a photon of light.
And because different elements have different orbital distances, the energy they release is completely unique.
Yes. The distance the electron falls dictates the exact wavelength, the color of the photon emitted. It is a luminous atomic fingerprint.
That's incredible.
Lithium impurities will emit a brilliant, distinct crimson red light. Potassium will flash a soft lilac purple. Calcium will burn a harsh brick red. By capturing that light and running it through a spectrometer to analyze the exact emission wavelengths, the chemist isn't just guessing. They're looking at the quantum signature of the contaminant.
It is absolute precision. And it's that level of microscopic precision that allows for its most historic macroscopic applications. Because as we trace the history of this molecule, it represents an incredible symmetry of human survival.
It really does.
Before we had quantum spectroscopy or Solvay plants, ancient Egyptian embalmers were harvesting naturally occurring natron from dry lake beds. Natron is a crude, naturally occurring mixture of sodium carbonate and sodium bicarbonate. They packed the bodies of the pharaohs in it for mummification. And looking at the chemistry we've covered today, it makes perfect sense.
They were utilizing its dual properties without understanding the molecular mechanics. The hygroscopic nature of the salt aggressively absorbed the moisture from the tissues, severely dehydrating the body to halt bacterial growth.
Like a desiccant.
Simultaneously, the inherent alkaline nature of the bicarbonate neutralized the highly acidic byproducts of decomposing flesh. It created a harsh, arid, pH-stabilized environment where decay simply could not occur.
It was a chemical time capsule for human biology. And then, millennia later, that exact same chemical mechanism is launched into the cold vacuum of space.
Let's go back to our starting point, Apollo 13. 3 men suffocating on CO2.
The lithium hydroxide scrubbers were exhausted. But the chemical imperative remains the same. You have an acidic gas, carbon dioxide, dissolves in water to form carbonic acid, and you need a base to neutralize it and pull it out of the atmospheric solution.
It's the Brunstad-Lowry theory again.
Sodium bicarbonate chemistry is the fundamental architecture of environmental scrubbing.
It pulls the toxic gas out of the air, trapping it in a stable carbonate form. A chemical mined from ancient riverbeds, utilized by the pharaohs to preserve the dead, and millennia later, harnessed in improvised plastic bags to preserve the living in lunar orbit. It highlights the absolute universality of chemistry. The molecular rules of engagement, proton donation, endothermic decomposition, specific gravity do not change, whether that molecule is sitting in an ancient desert tomb, aerating a cake in a modern bakery, or orbiting the moon.
Which brings us to the final thought of this deep dive. We have unpacked a truly dizzying array of scientific domains today. We went deep into the endothermic thermodynamics of laboratory neutralization and the calculus of the beta capacity.
We explored the dynamic buffering of MCT transport mechanisms inside the skeletal muscle of an athlete.
We dissected the chemical inhibition of free radicals in fire suppression engineering. We mapped the temporal dynamics of double-acting baking powder, and we illuminated the quantum leaps of electrons in emission spectroscopy.
All of this complexity, all of this utility, united by a single, humble, microscopic arrangement of atoms, NaHCO3.
It is a profound reminder that overwhelming complexity often hides within the most mundane simplicity. And I want to leave you, the listener, with a final mind-expanding concept to ponder regarding the global carbon cycle.
The journey of the atom.
Yeah, think about the carbon dioxide that you are exhaling right now, the literal breath leaving your lungs. That specific carbon atom could float out of your window and be captured by a blade of grass during photosynthesis.
That grass could be eaten by a dairy cow.
And the carbon integrated into the fat of the milk it produces. That milk could be fermented into acidic buttermilk, which you then purchase, take into your kitchen, and mix into a bowl of flour along with a spoonful of baking soda.
The acid meets the base.
The thermal decomposition triggers in the oven, and as that cake rises, that exact same carbon atom is violently released back into the atmosphere as CO2 gas.
Or conversely, it could be scrubbed from the dying air of a crippled spacecraft by that very same molecular structure. Sodium bicarbonate is not just a commercial product you buy in a cardboard box for $1. It is a fundamental mediator of the Earth's biological and atmospheric engine.
It balances the acidity of our oceans, it artificially buffers the blood in our veins, and it captures the exhaust of our civilization.
Exactly.
So challenge your perspective. The next time you open your refrigerator and look at that plain yellow box sitting in the back, which, by the way, the exhaustive data suggests might actually just be an old wives' tale for deodorizing anyway, don't look at it as a simple, boring white powder.
It's so much more than that.
Look at it for what it truly is: an intricate, highly reactive masterpiece of molecular utility. It is a chemical chameleon that quietly holds the extreme physical forces of our world together.